Welcome to Aethair Talks, where we explore the intersection of technology, policy, and the air we breathe. I am Vasilios Nasis. In each episode, we dive into insights, innovation, and ideas that are shaping the future of environmental intelligence. From air quality and data to regulation and real world impact, this is where meaningful conversations begin. Today, I'm joined by Dr. Peter Morris, the head of sensors at Ion Science. We discuss VOCs, or volatile organic compounds, why high quality sensors matter, the value of rigorous scientific testing, and how Ion Science is pushing the boundaries of sensor technology. Hi, Peter. Welcome to Ether Talks. Thanks for your time today.
Yeah, great. Thanks for the invite. It's a real pleasure to be here. I know we've spoken a lot recently over video call, and we've managed to discuss a lot of things, but it's nothing like getting in front of someone and speaking with them and getting to understand them and their business more, and it understands how we can help you a lot more. So thank you for inviting us.
My pleasure. So, actually, tell us a little bit about Ion Science and what you do for Ion Science for our audience so they become a little bit more familiar.
Yeah, sure. So I've been with Iron Science for 15 years now. My background is in environmental science. That's what I did my undergraduate in, and I did my PhD in actually water rather than gas, looking at how organic acids interact with mineral surfaces, sort of affect dissolution rates. So I was always interested in sort of mass transfer, and there was an opportunity that came up in our department to start looking at how gases were moving in the subsurface back in 2009, and that type of application excited me, and that's also went from the water world into the gas world.
So, speaking of gases, right? So, you guys have built a whole fame around VOCs, volatile organic compounds, or some others may call them just VOCs, right? So tell us a little bit about, first of all, just so for our audience to become familiar with, what is volatile organic compounds? Let's start with the basic.
Yeah, that's a really good question. So I've been in the industry for a while, so we throw that term around, VOX or VOC. So we'll break it down. So VOC stands for volatile organic compound. So an organic compound is something that has carbon in. And the volatile part means it can exist in the gas phase in temperatures that are found on the Earth. So, sort of example I like to throw around that people are familiar with is a petrol spill. You spill some petrol on the floor, and you can smell it. So that means there's some in the gas phase, but there's still some liquid on the floor. So it's not a gas, it's not a liquid, it's volatile. You get some in the liquid phase and some in the gas phase.
So now, if I'm not mistaken, and the whole volatile organic compound space, there is about 200 and some gases that
Uh,
fall under that category. Is that
Yeah,
correct?
yeah, it's a very broad classification, and it's more than a few hundred. We're probably familiar with a few hundred. There's a few hundred that have particular health and safety concerns, but there's thousands. Um, at Iron Science, we've characterized the response of our sensor to about 800, but that's not an exhaustive list. So it really is very broadly any chemical that contains carbon with a boiling point above 20, 30 degrees. So it's a hell of a lot of compounds in there. They're everywhere in the environment. People sometimes get a little bit scared by the term VOC and being exposed to them, and in some cases that's right. But they occur naturally. They're man-made compounds as well. So, for example, nature uses them to communicate. When a plant gets bitten by a bug, it will release some chemicals to tell the plants to release a smell that the bug doesn't like as a defense mechanism. In other instances, plants will use them to attract bugs, like the nectar in a plant. That's a VOC.
Right.
It will attract a bee in, and it help the plants pollinate themselves. And humans, we use them to communicate, like pheromones, how we're attracted to each other. That's from a release of VOCs.
That's pretty interesting. I never thought of that, actually.
Yeah.
Now, having said that, and again, we're both coming from an extremely scientific background. So, a lot of people in the scientific community, eh, they they want to be very particular, right? They don't like the term VOC. They're like, this is benzene, this is that, this is. So essentially, then what is the addressable market or the addressable audience for this type of VOC sensors like the ones that Ion Science makes?
Yeah, good question. So the sensors that Ion Science provide are what we call a ball brush technique. They will measure lots of VOCs that are there. They won't measure VOCs selectively. And so the holy grail would be to be able to measure VOC selectively at the concentrations of interest in real time for low cost and something you can wear. So that's a quite a challenging set of questions for a small cheap sensor to address. So the way our sensors are used, they're measured as a total volatile organic compound type of sensor, so a real good screening tool. So our sensors, they will the response from them will be a summation of all the VOCs that are present, and some VOCs that are harmful in very, very low levels. So it's good to sort of uh, group up all those VOCs together and get a signal. Then if you are picking up that VOC concentration, and that's a VOC concentration of concern, that can allow you to then pull in another device. It's more expensive to use, more cumbersome to use, and you can get that specific measurement. So it's very often used as a screen to let you know if something's happening. And if you really want to know exactly what's happening, then you pull in another technique to complement it.
So, what is a dangerous VOC level?
Okay, yeah, good question. The concentrations for danger, they vary, and it's probably good to speak about the two effects that VOCs can have. That there's a health and safety aspect. So the safety aspect will come from VOCs to getting to a certain concentration, becoming flammable or explosive, and that's an immediate risk to life.
Hmm.
That's a safety issue, and that happens at concentrations with some gases down to a few thousand parts per million. Now, the other effect, those long-term low-level exposures can cause things like cancers. That's very, very low-level exposure, and that can be from sub-ppb exposures to chemicals like benzene and formaldehyde.
So, which means then that from a risk point of view, risk management point of view, uh, do you have you seen cases that, in other words, you are measuring very low levels of VOC at ppb level that it was raising a concern for people, but essentially with further analysis, it was the sort of safe VOCs,
Yeah,
right?
yeah, yeah.
And so that's the one scenario, or the other scenario, which is you were measuring very low levels again of ppm or maybe ppb, and they were not raising any concern, but they were actually very dangerous cases. In other words, how do you handle those type of scenarios with the screening sort of VOC sensors, as you mentioned?
Yeah, yeah, sure. A good question. So we operate in two spaces. We operate, well, primarily two spaces. We are into loads of weird and wonderful applications, but the two main spaces are um, industrial health and safety and air quality monitoring. On the industrial health and safety side, an approach that we use, we have our bull brush detector, which is called the 10.6 EV sensor, and we have a narrower range sensor called the 10.0 EV sensor, and that allows us to focus on the aromatic compounds more. So, for example, in petrochemical facilities, oil and gas facilities, there's a plethora of VOCs around, and the real harmful ones are the aromatic compounds. So we use the 10 EV sensor to chop out the longer chain hydrocarbons and allow us to focus on the 10 EV on the aromatics. Those nasty things that the 10 EV detects, screens out the other ones. And we have a little wearable device that's near the breathing space, and we set an alarm level on there, and that would depend on the sites. For example, we can set an alarm level of say 1 ppm or half a ppm, and when they get a hit on there, they remove themselves from that zone in case it's not safe, and then they will come back with a device that can measure benzene specifically. And if you're interested in benzene, and that can be done in two ways. You have a handheld device that has a pump in, and you put a pre-filter tube on there, and that will pull everything through apart from benzene, and then benzene goes to the PID sensor, and you specifically detect that chemical. That's sort of the traditional way of doing it. Companies are now developing chromatography systems, portable chromatography systems that can speciate fully. So not only benzene, they can do toluene, ethyl benzene, xylene, formaldehyde,
I see.
DMS. But those techniques, they take a bit of time to work. That single shot device takes a minute or 2 minutes. It's a bit cumbersome. You have to use a tube. The chromatography system, it can take 5 or 10 minutes to get to the chemical you want. So this is what I mean by using these techniques in combination. You have the real-time protection from the PID sensor, and then when there's a potential threat around, then you can go and get a device that can measure it specifically. And then if there is a hazardous chemical around, you take the appropriate action. Either you remain out of that area, or you put breathing apparatus on or other personal protective equipment so you can work in that space. And then typically you want to resolve that leak issue so you can go back to safe working conditions.
So, one of the questions I always had is why, for most of the PIDs specifically, um, you guys are using isobutylene as the test gas or the calibration gas. What's so specific about that? And by the way, in some other cases on the lower cost sensors, they're using alcohol.
Yeah.
So,
Yeah. Yeah.
enlighten us a little bit on.
Yeah, sure. So the reason isobutylene is used as a calibration gas is for a few reasons. The PID has different sensitivity to different VOCs, and isobutylene sits about in the middle. When we talk about using a PID to measure VOCs, we talk about a total VOC measurement, and really it's a total VOC measurement relative to isobutylene or isobutylene equivalents. So it's quite nice because it sits there in the middle of sensitivities. Then also gases have different linearities with the PID sensor, and isobutylene sits in the middle of that. So it's a real nice space in the middle of sensitivity and linearity. Other important factors: a lot of VOCs can be sticky. So if you think about your sampling train, if you've got a sticky VOC, it can get stuck in on the way into the sensor. So you have a low concentration to start with, and then it can desorb afterwards, and then you can have a high concentration or a long clear down. Isobutylene is not sticky; it gets in and out your system pretty quickly. And I guess most importantly, it's not hazardous at the concentrations that you calibrate with.
I see. So now the second part of that question was, what is your view when people are using alcohol versus isobutylene? And again, does this has to do with the sensor architecture, meaning the one can be a MEMS versus a PID, or there is something deeper into that?
Yeah, I don't fully know the answer to that question, just from the little bits that I do know. So the PID is sort of so low cost sensors for VOCs. You have PID, metal oxide, and electrochemical sensors. The PID is sort of the most established technique and the most sort of selective to VOCs and the most stable in changing environmental conditions, but it's the most expensive. So it's horses for courses. So outdoors for applications such as health and safety at demand accuracy, you're going to go with the PID. But perhaps if you go to indoor, where the environmental range, the sensor going to be exposed to is a lot less, you can use one of these other sensors. And I don't think the metal oxide sensors respond so linearly and so quick and as fast as a response to isobutylene as ethanol, which is why I think ethanol is used for calibrating the metal oxide
Mhm.
sensors.
So obviously we have experience, at Aethair with both type of sensors. The PIDs that we use, in the higher end instruments like the Pro, and the metal oxide that we use in indoor air qualities such as the IAQ. So now, one of the things with the metal oxide, generally speaking, and the lower cost sensors is there is the interference, right? So a lot of things can be classified as VOCs. Um, so is it that does it really make sense to monitor total VOCs indoors with low cost, or do you think that from your experience it may create a panic or a false impression for no reason?
Yeah, that's a good question, and I'm not just here to plug
Yeah.
the idea. I want to give a rounded answer with the knowledge that I have. Uh, I think it's horses for courses. In some instance, it's going to be okay. It allow you to know that something's happened. So metal oxide sensors are very good at differential measurement. They tell you that something's happened, but you're not sure what's happened. So use of them that everyone may be familiar with. You're in a car. and you're driving along the freeway and you come by and a car is kicking out some smoke and your air conditioning were changed from drawing air in to recycling.
Yes.
And that's a metal oxide sensor in that's doing it. It knows something's changed. So, okay, let's be safe. Let's switch to recirculate in the air so we're not bringing anything bad inside. So, it's a really good example. And you can apply that, I guess, to domestic and light industrial applications. So, if you want to crank up some ventilation, if something happens, it can trigger that. But in terms of what that number means in relation to exposure and health and safety effects, then that sort of link starts to break down.
I see. One and another thing that we have seen also with these metal oxide sensors and electrochemical is the fact that maintenance is less frequent as opposed to PIDs. So you may sacrifice accuracy, but you get the bigger, longevity as far as calibration, because calibration is a very important thing of PIDs, right? So, um, I mean, we have incorporate now on the Pro, the Ion Science PIDs, and uh, we frequently talk about what is the correct process, how soon they need to be recalibrated, how you can maximize the life of each calibration. I mean, those are important things that is not just a sensor that you just take and it works, right? I mean, in order for it to deliver, it needs to be properly calibrated and properly maintained,
Yeah.
correct?
No, correct. And that's one of the things we've been able to do this morning is have a good, real deep dive into how the sensor performs, how its performance changes over time, and start speaking about how to calibrate the sensor and calibration frequencies. Yeah, that's critical. Like I was saying before, the sort of background of these sensors is used for health and safety applications where you're protecting people's lives. So it's very important you're getting accurate data out of it, and that needs to be transferred into the air quality monitoring space as well. So yeah, calibration is critical. Calibration frequency is critical. Um, the lifetime of the sensor of our sensor is 10,000 hours. And what does that mean? That's the lifetime of the element that provides the high energy light to do the ionization. Um, and as we were speaking before, 10,000 hours would get you to a year, nicely in continuous running operation. But you can duty cycle the sensor to get longer life out of it. So to tie it into, you have to run on 4 to 5 years. And for clients like yourselves, where you're supplying equipment to be installed for long periods of time and
Yeah.
it's building your business model around long-term leases, it helps you guys use PID for those applications in a little bit more of an accessible and understandable way.
Yeah, yeah. I mean, that's extremely important, and not from a maintenance point of view, also from continuation on the measurements, right? I mean, one of the things for us that is extremely important is uh, move to continuous monitoring rather than a survey type of a thing, where people were used to have handhelds and take sample measurements, and simply because thermodynamics, right? Everything is continuous on a continuous flow. So, which means that the air mixes all the time, whether it's indoors, whether it's outdoors. So, we want to have continuous flow of that information. And you got to find the magic formula over there of how reliable this is going to be, how you can extend the lifetime of the sensor and yet maintain excellent results at all time, right? So it's a trick, it's a polynomial equation, that needs to be figured out. So it's awesome. Now let me, let's switch gears a little bit. And I want to ask you something that we have been investing a lot of time, money, and thinking over the past couple of years on this whole AI revolution, right? So, so as you know, Ether, is leading in that space from with its platform on the environmental intelligence side, and customers are using now our platform not just to see time series data that collected, but actually they're using platform to generate the reports, discuss with the built-in Noises GPT that we have built which is our own form of LLMs that essentially you discuss, you communicate with your data, and you ask questions your data. So, um, so on the IoT side, the Internet of Things side that we operate, AI has played a very dominant role. Okay, and if somebody doesn't adapt to that, essentially it's just going off the cliff. All right. Now, in your world, the sensing world, okay, how does the AI play a role? And and should we expect to see maybe something AI, incorporated on the sensors? I mean, we're already working on implementing AI on the hardware side of what we do. You know what I mean? So
Yeah, no, it's a good question, and it's something we sort of discuss at Iron Science and sort of work out, how can we use it, how we can apply it, and some areas where I think it could have value. It's touching back onto that conversation we're having about lifetime and calibration and maintenance. By characterizing the huge numbers of our sensors, we could start using AI to understand what the degradation of the sensor is like in different environments, and start applying a correction for that, so we could extend between calibration intervals. And another area we were speaking about earlier, in the PID, it's a total VOC measurement, and ideally people would like to get selective measurement of gases, or groups of gases. And I can see how by collecting data from multiple low-cost sensors, you could start getting a fingerprint of what gas combinations look like, and deconvolve that using AI to try and get some speciation done from these lower cost sensors. I think that could be a really exciting area.
yeah, and it's kind of a little bit of unknown what to expect out of it, right? I mean, in the end of the day, um, one of the most fascinating things that we have found out is that using AI and, you know, digging now into all this academic research that has happened for decades
Mm.
on different models, algorithms that they take low cost data, compare it to the high end, the reference instruments data, and then you have PhDs written all over the world about how to make a correlation and develop an algorithm. And now with the power of AI, you can do that just in a split of a second. So one of the things that we've seen is that we can make a low cost sensor really act like a reference instrument. Something that costs $600 can act like something that, um, like a $40,000. Now, one thing that I know from signal processing, my background in signal processing, is that if you have trained data, you can get the instrument to operate 100% correct. The problem is when you don't have trained data, when you're going out to uncharted waters, will it still maintain the same levels of accuracy? So, so it's a very, very interesting space at the very least in the sense of, how deeply AI can be incorporated in the hardware, right? So, so what is a little bit of the next plans of Ion Science? Obviously, you guys for how long is the company now?
Yeah, so the company's been going since 1989, and we were in a slightly different space when we started. We were in leak detection rather than gas detection. And in 1999, that's when we switched focus from leak detection to gas detection, in particular VOC detection. Yeah, like in that time, our journey's taken us from large handheld devices to the small sensors that you can incorporate in your products. So where do we? Yeah, good question. Where are we going to go next? So we miniaturized PID in 2007. It was our MiniPid 1 sensor. We had a lot of feedback on that, and in 2015 we launched our MiniPid two sensor, the key improvements were temperature stability um, and longevity. So we went from about a 4,000 hour lamp to a 10,000 hour lamp to help with the applications that you're using the sensors in outdoor air quality. Running temperature can vary a lot, and getting into that point where you can run the sensor for a year.
But by the way, sorry to interrupt you. You guys also had pioneered something with humidity compensation, correct?
Correct. Yeah. Thank you for reminding me. Yeah. The other key thing about monitoring outdoors is humidity can change, and historically PID was affected by humidity, and humidity can affect a
What levels of humidity, by the way?
yeah. Good question. So humidity can affect PIDs in two ways. You can get a false negative and a false positive. So that sounds pretty complicated. How do you deal with those two effects? Well, first of all, I sort of explain how each effect occurs and how we've overcome them. So humidity, false positives. So what happens within a PID? You have a high energy light source. In our case, say vac UV lamp, and that ejects high energy photons into our ionization chamber. In that ionization chamber, gas molecules diffuse, and if the ionization energy of the gas is lower than the energy of the light, it's ionized, and we detect the electrons. When you have water in the ionization chamber, it doesn't get ionized by the photons, but it absorbs them, so it reduces your ionization efficiency. So as humidity increases, your photo ionization efficiency decreases, and you see a decrease in sensitivity as humidity increases. So the way we overcome that, we have a very, very thin ionization chamber, and we have a membrane that sits on top of the ionization chamber, which does a good job at keeping most of the humidity out. So that's how we overcome the false negative. The false positive, that's a different effect. So in the ionization chamber, you have an anode and a cathode. Over time, VOCs enter the ionization chamber, and this photoionization breakdown product is produced. And over time, that can build up on the walls and between electrodes. But when the slight bit of humidity that can get in the sensor gets in, that breakdown products are fine particles, acts like a sponge, and it mops that water up, and it can create a bridge between the electrodes, creating a short circuit. And what we have in our design is what we call our fence electrode technology, and that sits between the anode and the cathode and mops up any stray current. And that's how we prevent false positives, which is absolutely critical for outdoor measurement.
Fantastic. So, last, thing I want to ask you is, you saw how we use the ion science sensors. Now, it's very different than most of the other applications in the health and safety because, from one point of view, our platform now with the Pro, it addresses the, health and safety sector, but also it addresses the publics, right? With citywide monitoring and so on. Um, and essentially makes even your sensor, you know, deliver data to the masses rather than to a very specific, audience. So, how did you, how do you like this approach?
Yeah, it's fantastic. So our mission is to protect people and preserve the planet. So this fits in perfectly. So yeah, the other application we spoke about, we're protecting the worker, and like you say, that's only a certain percent of the global population getting these sensors in devices like yours to protect the general public. That we're being able to use our sensors to protect everyone's life. So it fits with our vision perfectly.
Fantastic. So again, thank you for your time today. I learned a lot of things about your company. I'm sure our audience also learned quite a bit about the world of VOCs and what ion science does. So thank you for your time, and look forward to speaking to you again soon.
Yeah, great. Thanks for the invite, and really looking forward to working with you on your new exciting projects and working in real technical partnership by having the open conversations we've been able to have today.
Likewise, thank you, Peter.
Great. Thank you.